So the general idea again is that we're taking the log of both sides. All right, that step right there is what makes it log differentiation. All right, because everything else that you do after this is simply taking the derivative. All right, so if you're stuck at this point, it has nothing to do with the new concept. It has to do with either pre-calc or just general basic derivative taking, like product rule, quotient rule, chain rule kind of stuff. All right, so I'm going to clean it up. We're looking at, so when I take the natural log of both sides, I have my exponent. It's going to hop over to log. All right, so it becomes ln of x multiplied by the ln of x. And that's equal to ln of y. Right, now you could work with it like this. You do a little product rule. I don't want to do that. I'm going to write it as ln of x as a quantity squared. All right, that would not be power rule for logs. All right, that exponent wouldn't be able to hop, right? Because it's not just the x being raised to the second power, it's the entire thing. All right, but I can differentiate 1 over y dy dx. On the right-hand side, a little chain rule. 2 times ln of x multiplied by 1 over x. All right, and then final answer would be obtained, I guess, by multiplying everything by the y being x to the ln of x. All right, so I'm going to take this expression, whether you clean it up or not is up to you, but cleaning it up is not overly challenging. I'm taking that expression, I'll write it as 2 ln x over x and multiply it by the y, which is x ln x, x to the ln of x. All right, so we have our derivative there, and you could do something like make this natural log of x squared if you want, but why would you give up a constant multiple and make it a power? Does it make the question any more challenging? I don't know. I don't think so. But it's a constant multiple. If I needed to find the second derivative, I'd rather have it in that form than to have it as an x squared. All right. So a log differentiation problem involving a log. Turned out it's not too bad. Number 9. Did this one out on the board yesterday. And it took a fair amount of space to do, right? But it's the same general idea. You're going to apply log differentiation, so we're going to take the natural log of both sides. Right? Now, you may want to, it's up to you, you may want to try to clean it up a little bit first, if it's clean upable. Sometimes it is. We have something that could be thought of as an exponential equation or a log equation. So you have a couple of different pathways. Okay? You can work with it as is and just take the natural log of both sides, or you could try to manipulate it first and see what happens. Right? If that were the case, you might convert it to something like, like ln Wait, is it really ln of x plus y equals ln of 1 plus y? Huh. Look at that. All right, well, let me just do a little Lagrangian action for you. So a little mnemonic if you need it. All right, so it would be log base e of my exponent, which would be x plus y. Is it? Equals ln of 1 plus y. Ooh. Well, that's exciting. All right, another possibility would be to convert this as if it were a log equation, but then it would be e to the x plus y equals 1 plus y. I think that's probably going overboard. But you can work with it in this form or in this form. The benefit of working it in this form is that it's already in the appropriate form. The natural log has been taken. All right, so these are two equivalent equations. If I want to do it in this form, I'll do it in the black first. This is the way I did it yesterday. I'd be taking the natural log of both sides. So it would be the ln of the ln of 1 plus y equals, well, ln of e, that's inverse relationship, so that's just going to be x plus y, right? Because it's x plus y ln of e. Then I could differentiate. So it's chain rule gone crazy here. All right, so it's the ln of something, that something also being an ln. So 1 over the ln of 1 plus y times the derivative of the thing on the inside. All right, so the derivative of the thing on the inside is also natural log, which would be 1 over 1 plus y times the derivative of the thing inside of that, which would just be a dy dx. So a couple of things have to happen here. So let me get rid of this, because I botched that. Of course I did, because it's Friday. It's Friday. All right. So what do we say? 1 plus dy dx? All right. So then, all right, so a little bit more to it than I let on. So 1 over ln of 1 plus y times 1 plus y dy dx minus dy dx. We want to consolidate our dy dx's. We have a common dy dx for each term, one here and one here, so factor it out. Oop, a bracket is what I'm going with here. Now, on that I can't control. Like, it tends to help, because then people will be like, "Oh, I want to give you a call at your classroom. What's your extension?" I don't know. Unfortunately, you're not going to be able to call me. So, so what I was going to say before all that was, depending on the nature of the question, if I don't have to simplify too much, then I could just take one and put it over this disaster of an expression. But again, you never know. It could be a multiple choice question. So let's get a common denominator to be 1 minus ln 1 plus y times 1 plus y all over ln of 1 plus y times 1 plus y. Yeah, I like it better when I screwed it up and made it much easier. Yeah. Multiplied by the reciprocal, ln 1 plus y times 1 plus y all over 1 minus ln of 1 plus y times 1 plus y. All right, so what we have here is, it's known as a differential equation. Any dy dx equation. I mean, sometimes we go out of our way to make things sound fancier than they need to be. But any dy dx equation is known as a differential equation. This one is specifically in terms of y. And so is that a good thing or a bad thing? It's a thing, and it doesn't really make a difference. You could have it in terms of x, you could have it in terms of y. You could have it in terms of both x and y. It's all dependent on what you need it for. Now, if you have a differential equation that's solely in terms of y with no way in which you can come up with the value of y, then it's not overly useful. But we're actually going to work with equations like this in the second semester and be able to come up with the graph of this differential equation without having any sense of what y is. So just through direct substitution doesn't seem like it's overly useful, but it will be. And you actually have a nice little program in your calculators that'll help you evaluate those. It's called slope fields, but that's a different story for a different semester. All right, anyway, so second attempt on simple pre-calc, converting from exponential to log form because for whatever reason I couldn't do it before. Brain cramp. E to the x plus y equals ln of 1 plus y. I mean, there's a lot going on, but that's still no excuse for me. So I have my d, I have my n, and I have an a. So log base d, so that's ln, of the a, so ln of ln, 1 plus y, equals x plus y. All right, so you get it in this form, and then you hope that it'll make your life easier, but then you realize it's exactly the same as what you would get if you were to take the natural log of both sides and then simplify. All right. So then an alternative way to do it, an alternative to the alternative, because again, our goal in doing any of this is never to make our lives more challenging, like, oh, let's just do it 3 ways for the hell of it. Our goal is to try to manipulate it in such a way that we can come up with an easier approach. So let me rewrite it as ln, so it's the original form, ln of 1 plus y equals e to the x plus y. I'll make that log base e of 1 plus y equals e to the x plus y. And again, every stage of the game here, we're just trying to make a determination of, will this form make my life easier? If it does, then we go for it. If not, then we don't. All right, here, what I would be doing is converting into exponential form. Yeah, same idea. I have a d, an a, and an n. So I need d and a. So e to the x plus y equals 1 plus y. Now, if you're required to use log differentiation, then you have to take the log of both sides, in which case you're going to undo everything you just did. So it defeats purpose. But if you have the luxury to do it any way you want, then you may consider doing it this way. Because then, using explicit methods, I could say y equals, well, part of it would be explicit. I could write it as y equals e to the x plus y minus 1. I'll have dy dx. You really don't even have to worry about the 1 because it's going to go away anyway. Exponential e, rewrite, multiplied by the derivative of your exponent, and then multiplied by the derivative of that exponent, which would be a 1 plus dy dx. All right, so in the housekeeping portion of this, I would get dy dx equals, I can keep the base and add the exponents here. It would be e to the x plus y plus x plus y multiplied by 1 plus dy dx. This is really just for fun now, because it doesn't take too long before you realize you would never want to do it this way, but it's just cool to look at. Yeah, it is. I mean, math cool. Yeah, not real cool. Nothing.
Yeah.
Yeah. I mean, it's the rarest of instances where, like, an event in math class transcends like math cool to become real cool. It's the rarest. So, but look at that.
Is it supposed to be a wave?
Then I gotta subtract, factor, and this is great. It is, right?
It's like a sine curve, but in an equation. The equation itself is the sine curve.
We just have that.
So subtract and factor out your GCF, and you get this. And then our final answer, which would look absolutely nothing like the answer that we previously got, but it would be equivalent. Would be that. All right, so the hope that you'd end up with something simpler was quickly crushed. But you would realize that early on. You know, you convert it over, you get to this portion of the problem right here, and you say, all right, well, the hell with this, I'm not doing it. Like, this is going to be, it's not going to clean up nicely. So I'll just kind of grin and bear it and just deal with the other approach. But you're screwed one way or the other. Yeah. You're in for a ride one way or the other.